When I'm recording this, which is what I'm doing right now, sometimes PowerPoint tends to bog down and take a while to advance slides. So apologies for some of those interruptions. So without further ado, we'll get started with just a very, very brief introduction on Zyxel and who we are, in case you're not familiar with us. There we go. So we've been around since 1989, so 30 years of business making networking equipment. We started off in the days of bulletin board systems and dial-up ISPs, making the dial-in modems that your service provider would use that you would dial into from home. From there, we expanded into DSL products, ISDN products, cable modems, and from there into stuff designed for the central office. So metro area switches, things like that. And nearly 20 years ago, we jumped into the SMB business networking segment, and we've been here ever since. We've got 1,500 employees around the world. We've got over 100 million devices deployed out in the field. So today's webinar, we're going to be just going through some of the basics of wireless and how it works. We'll start off with some of the very basics, and towards the end here, we'll get into some tips and advice for different use scenarios. So the first thing to talk about is there's some confusion when we talk to people out there about who does what when it comes to Wi-Fi. So the IEEE group, international engineers, whatever it is, they create the standards. So that's where the 802.11, 802.11b, 802.11ax, that's where the 802s come from. That's how they classify the different standards to make them easy to look up. Basically, it's a group of chipset manufacturers, hardware manufacturers, and whatnot, all coming together and creating the standards for what will become the various Wi-Fi standards going forward. The Wi-Fi Alliance is another group. It's primarily the manufacturers, and they try to fill some of the holes in IEEE and try to work primarily on interoperability. So even though everyone's maybe following the same IEEE standard, you know, even after the years and years of debate and revisions, there's still parts of the standard that are not as well defined as they could be, and you might end up with Qualcomm implementing it or interpreting it one way, Broadcom interpreting it another way. So the Wi-Fi Alliance is there to sort of smooth those out and make sure everybody's devices talk to each other. The Wi-Fi Alliance is the one behind the idea of renaming 802.11ax to Wi-Fi 6 and retroactively renaming the other versions of Wi-Fi to Wi-Fi 5 and 4 and stuff like that. And then the FCC, it's our government. They're primarily focused on output power and spectrum usage. So they're the guys who make sure we're not pumping out too much power out of our devices. They're making sure that we're not bleeding over into other spectrums where we're not supposed to be playing. So let's talk a little bit about radio waves. As a general rule, as a frequency goes up, the more data that can be encoded onto that data or onto that frequency. But at the same time as the frequency goes up, the range gets reduced. As you get up to higher and higher frequencies, the signal is more readily absorbed or blocked by just the air itself, by walls, by building materials, people, things like that. For those of you that are older, you might remember the good old days of when cordless phones were first out, and you used to be able to take your cordless phone, walk out of your house, walk down to the end of the block to your friend's house, and you could still be holding a conversation. Then phones moved in the 90s from 900 megahertz, or I think in some cases maybe 700 megahertz. They moved up to 2.4 gigahertz. So what happens is we increased the frequency, the sound quality got better and more clear, but the range dropped. So now instead of walking down the block, maybe you could walk out to the edge of your yard and be able to still maintain a conversation. Sort of the late 90s, we started seeing at least some phones moving to the 5 gigahertz spectrum. And again, you should have got an increase in your sound quality, but the range reduced. So that's what's going on there. So most radio frequencies, or all radio frequencies, are regulated by the FCC. Most devices require a license. Some cases those licenses can be quite expensive, such as the frequencies used by standard cell phones, TV stations, radio stations. Some cases are a lot more affordable, such as Citizens Broadband, CBRS. So they have carved out the little areas of frequency that can be used by anybody. So there's a little chunk of the 900 megahertz frequency, a little chunk of the 2.4 gigahertz frequency, and a chunk of 5 gigahertz that are open. So you can be used without a license. The trade-off being anybody can use them. And other than following some output rules and interference rules, all those devices have to play nicely with each other, and it's up to the individual vendor to make them do so. So the next thing I want to talk about is output power, the power of the signal. So a lot of people love to use milliwatts and talk about, oh, I've got a 200 milliwatt radio, I've got a 4 watt. Generally, though, in the industry, what you'll see normally on the spec sheets from anybody that's creating products aimed at the business space is dBm instead. And there's two reasons for doing that. One is dBm makes it really easy to add antenna gain. So you can just take your dBm and add your dBi, and that tells you what's going on. You can't do that with milliwatts. The other thing going on with dBm is your radio power decreases rapidly in space. I want to say it's an inverse square. It's not quite accurate, but think of it that way. So dBm is more of a square-based thing, so it makes a lot more sense. It's a much more reasonable comparison. So for instance, 20 dBm is 100 milliwatts, 23 dBm is 200 milliwatts, and you go, wow, you get twice the range, but in reality, you don't. It's actually a much smaller increase in range that you would see. So 20 versus 23 is a much more easy to concept or much more representative of the performance increase you might see versus looking at the milliwatt side of things. So the next thing we want to talk about, and this is probably the most important thing when it comes to your wireless performance that no one pays attention to, and that is your signal-to-noise ratio. So that is the ratio between the signal that you want to see, the data that you want to see, versus all the other interference and other things using that same spectrum. So the signal-to-noise ratio is really what determines how good your Wi-Fi signal is, and how much data you can pump through, how few packets need to be retransmitted and things like that. So when you're looking at equipment, it's really important to look at the receive sensitivity, and when you're doing site surveys, it's really important to use a tool which shows you that signal-to-noise ratio, not just the signal strength. Attenuation, that's basically how much the signal degrades over time. And as I talked about before, Wi-Fi signals, the power degrades really quickly. There's a lot of media out there which will absorb or block or reflect the signal. So these are some examples here. Standard window will give you a 3 dB loss in your power. A tinted window, particularly if it's using some sort of metal to reflect the light, that can give you up to an 8 dB loss in your signal strength. Walls, depending on what they're made of, can be anywhere from 10 to 25 degradation in the signal strength. Floors, whether they're made out of concrete or not, will also have some pretty big hits for you. So it's just showing, giving you some rough ideas of how different materials are going to degrade the range of your wireless. Another really important thing, well, actually, before I go back, let's go back. Also, if you're wondering just in the air how much it degrades, up at the top there, underneath where it says path loss, that is the formula you need to calculate the distance that you can get, assuming there's no other interference, no obstructions. So as you can see, it's not necessarily the easiest thing to calculate your range. And that's, again, ignoring loss caused by degradation, reflections, or dealing with signal-to-noise ratio, the noise floor. Anyway, so another thing to think about when we're talking about Wi-Fi range is that Wi-Fi is two-way communication. It's just like I'm talking to you in a room. If we're talking to each other in an empty room, we can hear each other without having to raise our voices. If we move into, say, a party where there's music playing, we might have to get closer to each other and have to shout louder to be able to communicate with each other. And also, more importantly, if one person is having to shout, but the other person maybe has a sore throat, they can't shout, you can't have effective communication because, well, one person is able to hear just fine. The other side of the conversation can't hear what's being said back, and it screws things up. So that's something very important to keep in mind. You know, a lot of access points out there, 200 watts, 500 watts. If you throw in the antenna gain, you can get up to 4 watts of power on some of your heavier duty access points. But if you're using an iPhone, you're lucky if you've got 25 milliwatts of output power. So you can see that, you know, having this really powerful access point, it's sending its signal really far, but it does you no good if the access point can't hear the signal coming back from the client device, whether it's a phone or laptop or what have you. So you need to keep that in mind. And that's also one of the problems we often run into is people go, well, my phone shows I've got 3 bars of Wi-Fi strength, yet my internet's barely functional. Why is that? And the answer is because your phone is showing you how good of a signal it's receiving from the access point or your router, but it's not showing you how whether or not that access point or router is able to hear the data you're sending back to it. So the handshaking is failing, things like that. So it's really important to keep in mind. This also deals with, when we start talking about later here, we start talking about interference. So your access points are pumping out this huge amount of power, and they end up interfering with each other even though they're a long ways away. So something else to keep in mind. Another thing when we're talking about Wi-Fi and how it behaves is we have to understand here that as the signal goes through objects, it will diffract, it'll degrade, but also the signal is bouncing off of things, particularly metal. So it can be bouncing off of things and changing the angle. You can get what's called scattering. You get into a situation here that we like to call multipath, where the same signal is bouncing off of different objects in the environment. So your receiving device is actually receiving the same signal from multiple directions, slightly offset from each other because they've traveled different lengths of distances. We'll talk about more about that a little bit later in a few other slides. Another really important thing to talk about and consider when you're talking about Wi-Fi is that only one device can transmit at a time. The one exception, and we'll talk about that later, but generally it's just like your old walkie-talkie radios you had as a kid. If 2 kids try to talk at the same time, they interfere with each other and you just get a bunch of loud noise that you can't make sense of. It's the exact same thing with Wi-Fi. If 2 devices try to transmit at the same time, they'll interfere with each other, and neither of them will end up being able to send the data they wanted to send. So this is showing here, this is the standard with 802.11, A, B, G, N, etc., how it works. And basically, the device, before it transmits, will stop and listen to see if anybody else is transmitting. If nobody else is transmitting, it will then send the data it wants to send. Alternately, if somebody is transmitting, it will back off using a little randomized number of how long to wait, and then it will check again to see if anybody else is transmitting. So this works pretty good back in the days when we invented this, when we weren't sending that much data over your Wi-Fi, and it didn't need to be that reliable. Now that we're streaming video, and now that we're streaming, doing, voice over Wi-Fi, and it's really important that no packets get dropped, that you're not backing off too long before transmitting, because then the packets get delayed and you get gaps and things like that. And this comes down to which is probably the most common question we get asked, which is, well, how many devices can I put on your access points? The number of devices realistically has nothing to do with the access point itself. Instead, the limiting factor is going to be the 802.11 protocol itself. Because what happens is if you get too many clients, or too many clients that are broadcasting a lot of data, such as streaming or voice over Wi-Fi, what happens is 2 devices will decide at the same time they want to send data. They'll both check, nobody else will be sending data, So they'll both decide to then send data and interfere with each other. So what happens is most access points these days will claim anywhere from 64 to 128 to 256 client devices. Most of our business APs will claim up to 256 client devices. Most of our competitors do as well these days. But if those clients are actually doing anything and actually sending data, they're going to be stepping over each other when it comes to the airtime, and they'll end up interfering with each other and degrading the network greatly. So you don't actually want the maximum number of clients. And again, it's not the AP's fault or your router's fault. It's the protocol itself and the way that these devices decide if it's okay to send data or not, causing interference when you've got a crowded network. The other thing we've got out there, which is related to this, is what's called the hidden node problem. And basically, this comes down to a similar thing, which causes two devices to transmit at the same time. And what happens is you've got an access point in the middle of your ceiling. As we talked about before, your access points generally have more power than the clients. So it's got a nice big circle it sends out of coverage area. What happens is your client device, which is lower power, it has enough power to send its signal back to the access point, but it doesn't have enough signal to send its signal to another client device on the other side of that coverage area. So what happens is the client device won't see the other client devices transmitting because it's out of range of that client device. So it'll start transmitting, and it'll screw up your access point or your router because it's in the middle and it's able to hear from both of them at the same time, and then the signal interferes with itself. So that's what we call the hidden node problem. So the other thing I want to talk about here is data rate versus throughput. These two terms often are used interchangeably, and depending on who you're talking to, if they're not using them interchangeably, how they define it may vary based on who you're talking to. So I'm going to try to use the terms as we most often see them on advertising material for Wi-Fi devices. So the standard way to talk about Wi-Fi speeds is to use the data rate. So this is the max amount of data that's being transmitted between the two wireless devices. You will also see this referred to as the physical rate or the link rate, depending on where you're looking and who decided to define it. So this includes not only the data you want to send from your application, this includes all the protocol overhead that goes into making this work. So your TCP overhead, your UDP overhead, and in the case of Wi-Fi, the protocol overheads that allow Wi-Fi to work. And then you'll see what is normally called throughput. And when people are talking about throughput, normally what they're doing is they're opening up a web app or they're, a web browser and opening up speedtest.net and doing a speed test that way. So they're only seeing the data that's being sent between the distant server to their web browser. They're not looking at all the other data that's being sent. And so what happens is when we're talking about an environment such as Wi-Fi, which is really noisy, really crowded, in order to make it work, we have to put in a lot of additional overhead to create a reliable connection. And so because of that, depending on which Wi-Fi standard you're using, it's very normal to see easily a 60% difference between the data rate, which is including everything, and the actual throughput, which is what you see when you do a test on speedtest.net or do an FTP transfer between two sites. So a good example of this, and these pie charts are kind of made up just to illustrate the point, but with Ethernet, it's a fixed cable purpose-built for only transmitting data. So there is very little overhead. So the amount of throughput that you would see with a speed test or an FTP transfer is very close to the advertised rate. So if you've got a 100 meg connection, you're going to get really close to 100 meg throughput. With a gigabit connection, you should be able to get really close to a gigabit throughput, provided both ends of that you're testing have the ability to hit those types of speeds. With the Wi-Fi, you've got to deal with retransmissions due to interference and SNR issues. You've got to deal with the protocol through overheads of the Wi-Fi protocol itself that makes Wi-Fi possible. So you'll see a huge decrease in the throughput as you measure it because you're not looking at what else is going in and being consumed by the data rate. So I hope that makes some sense. So the next question is, well, how do you increase speed when it comes to Wi-Fi? You know, and I'm looking at this from a manufacturer perspective, not from a user perspective. So the way that traditionally this has been done is to increase the QAM level of the encoding. So 802.11n was 64 QAM, 802.11ac is 256 QAM, and now the new 802.11ax stuff out there is 1024 QAM. So that's how much data can be encoded and forced into the same amount of spectrum. The other thing we can do is increase spatial streams. And we'll talk a little bit about more what those are in a minute here. But if you look at a lot of business APs, rather than advertising themselves as AC 1750 or AC 3000, you'll see instead 1x1, 2x2, 3x3. So that's talking about spatial streams. And we'll explain that a little bit more in a minute here. The other thing you do is you increase the bandwidth. You know, 802.11g, each channel was 20 megahertz in width. With 802.11, we had the ability to use 40 megahertz channels. So doubled the bandwidth that we could use on a single channel. With 802.11ac, we went up to 80 megahertz channels, and in some cases, you can go up to 160 megahertz channels. That's how you get those faster speeds. So we will come back to those here in a minute. So I want to talk a little bit here about Wi-Fi and bandwidth. So the first thing to talk about here is when we're dealing with the 2.4 gigahertz spectrum, we've actually only got a little chunk of spectrum that realistically the usable spectrum is around a little more than 60 megahertz. So in the US, we've got channels 1 through 11, and this causes a lot of confusion for people who are new for Wi-Fi, because they'll say, oh, my neighbor's using channel 6, I'll use channel 7, there won't be any interference. The problem is these channel definitions were defined long before Wi-Fi came around. So they're based on different widths. So the actual Wi-Fi channel being used is around 22 megahertz in size. So with a little over 60 megahertz available, that means you can only use 3 different devices before you start interfering with each other and having to use the same frequency amongst multiple devices. So what happened is at the end of 802.11g, there was the G plus stuff, and 11n came out, and the way they doubled the speeds was by increasing the bandwidth from 20 megahertz to 40 megahertz. Which is great, you've doubled your speed that you can theoretically get, but you've only got 60 megahertz available. So what happens there when your neighbor wants to get on and they want to use 40 megahertz? And the answer is you get interference. So you either deal with the interference and the increased rates of retransmissions required due to packets being dropped, or you program your device so it automatically drops back to 20 megahertz mode. Because otherwise, as soon as you add a second device, no matter what it is, you're going to get interference if you're using 40 megahertz channels. 5 gigahertz is a little bit better. So we've got on there right now is showing you, you know, with 20 megahertz channels, you've got what appears at first to be a lot of channels available there. You'll notice some of those are colored in orange and we call DFS channels. I'll explain those here in a little bit. But this was why there was a big move to 5 gigahertz. You've got a lot more frequency in theory or spectrum that's available for you to use. So those DFS channels, that part of the 5 gigahertz spectrum is used by radar systems, both military, airport, weather radar, all use those channels. And because Wi-Fi is kind of late into this space, the radar gets priority. So if you're using DFS, what happens is your device periodically checks, and if it detects that radar is being used on that channel, it turns itself off. Some devices won't actually turn themselves off. Instead, they'll change the channel they're using. They'll try to find a channel that's not being used and then start broadcasting on that channel. So that's one of the problems we'll hear from people is, hey, my wireless signal is really intermittent. It doesn't seem to be working that well. There's this AP is defective. And no, generally what the answer is no. You're using a DFS channel. Your AP is detecting that something else out there is operating on the radar. It's detecting someone's using radar, so it's shutting itself off and kicking everyone offline. So that's what's going on there. The other problem we run into is when you're in a business environment where people are bringing their own devices, or in particular in home, is that a lot of consumer equipment doesn't support DFS. So you've put your router or your access point onto a DFS channel, but Bob in accounting, his cheap phone that he brings from home, it doesn't support DFS. It's really common on consumer equipment because getting DFS certification takes a long time. And in consumer space, everyone's really killing themselves to be the first to market with whatever the latest technology or chip is. So oftentimes they rush the product out before they can get the DFS certification. And oftentimes they never even get around to adding the DFS certification, or they do get it, but then the device needs a firmware update, and consumers tend not to update their firmware. So for a lot of reasons, because of that, you maybe don't want to use these DFS channels. The next thing that happens is, well, what happens if we go up to 40 megahertz channels? So suddenly, if you look just at the green section that isn't DFS, you're now reduced to just 4 devices, 4 different access points, 4 different channels available that you can use before you start having to overlap and interfere with each other. But as I talked about before, you know, with 802, the latest version of 802.11 that's out there, we're all using 80 megahertz channels to get those speeds that you see advertised. So again, now you've doubled the bandwidth you're using, so now you're down to just 2 channels, non-DFS, that you can use before you're interfering with things. So now you're back down to the same situation you are with 2.4, where you can only have, you know, a couple APs before you start dealing with interference. And with 160 megahertz channels, you're down to the point where you have to use DFS space to be able to use them. Okay, so that's bandwidth and how that works. So next up, we'll talk about spatial streams. So as I was talking about before, the wireless signal is bouncing off of various objects around the environment. And what happens is that means that the signal is coming to your receiver, the device is trying to receive that signal from multiple different paths. And because the lengths and distances are long, they're coming in at slightly different times. So this causes interference, and historically has caused issues with reception capability. You know, trying to deploy Wi-Fi back in the 802B and G days in an environment where you had metal shelves or industrial equipment was horrible because of this multipath issue. So what happened is some smart people out there started saying, well, maybe we can use this multipath problem and actually make it a benefit. So one of the first guys that did that was a little subsidiary of Zyxel called Zydas. So we were one of the first vendors out there to make a chip that actually turned multipath into a benefit. And eventually we sold that off to Atheros, which was then bought by Qualcomm. So now Qualcomm's using our tech. But it's a big part of how 802.11 and 802.11ac and 802.11ax are now working, is we've taken this multipath problem and we've turned it into a benefit. And so what we've done is, what we've found is we can send different streams of data simultaneously on the same channel, and we can use this multipath, a way that the signal bounces off of different objects and comes in at slightly different offset times, and we can use that to basically double the amount of data. So basically, instead of just having 150 megahertz, we can now send, if we had a 2x2, so 2 spatial streams, we can have a situation where we've doubled our bandwidth. We can send 150 megabits, the theoretical maximum on that channel at that time, on one antenna, and send a different 150 megabits on a different antenna. And the client device that supports MIMO is smart enough to take those 2 signals and combine them together and tell them apart, even though they're operating on the same channel at the same time. So you get improved throughput. The other benefit you can run into is something called multi-user MIMO. So with multi-user MIMO, we're using these same spatial streams, but instead of sending different data on each stream to one device and then having that device combine them together for one faster connection, you can use this to send data to multiple devices at the same time. So this is really ideal in environments where you've got a 4x4 or a 6x6 or an 8x8 access point, but most of your client devices are 1x1 or 2x2. It allows you to send data to multiple devices at the same time, making more effective use of your airtime. So when you're looking at business class access points, as I talked about before, instead of seeing AC 1750 or whatever being advertised, instead you'll see 2x2 or 3x3 or whatever. So what that's telling you basically is how many spatial streams you can support or how many antennas you have. So the first number is the transmit antennas. The second number is the receive antennas. And generally, these are going to be the same. So you'll see 2x2, 3x3, 4x4 on access points. On client devices, sometimes you run into a situation where you'll get a 2x1. So it's got two antennas, or actually, excuse me, a 1x2. So you've got one antenna for transmitting data, but you've got two antennas for receiving. So you can receive two spatial streams, but you can only transmit back one spatial stream. And if you look at Cisco equipment, you'll see something kind of weird where they'll say 4x4, then there'll be a colon and then like a smaller number, like a 3. They'll say 4x4 colon 3. So that's telling you they've got 4 antennas they can use, but they can only actually use 3 of them at a time. So they only can actually really support 3 spatial streams. So it's not really a 4x4. But so if you see that 2x2 colon 1, that tells you it's really only 1 spatial stream, or 3x3 colon 2, it's really only 2 spatial streams they support. The benefit of that extra unused antenna is it gives the device a little flexibility as to which, you know, in a 4x4 3, which 3 antennas it's actually using. So in theory, it can change based on the actual RF environment. It made a big deal back in the early days, but these days with anything 802.11 AC or better, it really doesn't make that much benefit to have more antennas than you have spatial streams for real world use case scenario. So now to put that all together, bumping up speed, we've got this little chart here showing you the QAM type, number of spatial streams, and how many, what the bandwidth you're using is. So you can see the different speeds that are available for you. So you see here a spatial stream, 2 spatial streams, 256 QAM, and using an 80 megahertz channel gets you an 866 megabits throughput, or we would probably call it AC 900. That's your maximum speed. But again, if you don't have that bandwidth available and you drop to 40 megahertz, you see the speed drops down to 400 megabits. If for some reason, based on signal strength, you can't do 256 QAM, you've got to drop down to 64 QAM. Now you drop from 400 megabits throughput to 300, et cetera. So you can see based on what you're doing, how that affects the speed and how really you need all of your ducks in a row, spatial streams, modulation type, bandwidth availability to be able to hit the maximum speeds that you're going to see advertised on new devices. So I already talked about this, I guess I got ahead of myself here, but how many devices can you get on one access point? It generally is not a limitation of the access point, it's a limitation of the 802.11 spec. So what's going to determine it is going to be how many spatial streams do my client devices support? What's my signal to noise ratio or my signal strength? What's my bandwidth utilization? How am I using 20 megahertz channels? Are they connecting at 80 megahertz channels? That's going to decide what you can do. So in this example we've got up on the screen, we've got 3 different types of devices. All of them are are transmitting a stream at 3 megabits per second. So in the case of a laptop, it supports 3 spatial streams. What we see here is we can utilize around 77% of the available airtime. And we can get ourselves up to 100 megabits of total throughput with 34 laptops on that device. That's really good, right? Now we go to a tablet. Again, basically same theoretical signal strength, but we're down to 2 spatial streams. And now what we see is, again, with the same amount or the same speed, we end up in a situation where we can only get 21 tablets on there versus 34 laptops. And the overall data that we can push is only 65 megabits versus 100 megabits with the 3 spatial streams because of the more effective utilization of the airtime. And then if we go to a cheap smartphone that only supports 1 spatial stream, again, using the same type of simulated traffic of a 3 megabit stream, you're only going to be able to get 10 devices on that access point, and 30 megabits overall throughput. So again, it's the 802.11 standard, and it's the environment itself that's going to determine how many devices you can get on that access point and what type of traffic you're using. That's going to determine it. You know, if you've only got guys who are browsing the web and reading web pages, that's, you know, they're not very active, they're not using a lot of airtime. You'll be able to pack a lot of guys onto that access point. But if they're streaming Netflix and they need 6 megabits dedicated throughput, suddenly you've got a lot less devices you can fit on there. And if you've got something such as the device doesn't support a lot of spatial streams, that will decrease how many devices can fit on that access point. If there's a poor signal-to-noise ratio and you're having to retransmit, that'll affect things. If, because of interference, you've had to drop from 80 megahertz channels to 20 megahertz channels, that will reduce how many devices you can get on there streaming Netflix before you have issues. So we've been talking a lot today about the effect of interference, and I want to go a little bit more into that for you. So you'll see the term most commonly used is co-channel interference, or CCI. So this is basically interference between any 2 devices operating on the same frequency. So as we've talked about before, you know, there can be 2 devices transmitting at the same time onto the same access point. It can be multiple access points deployed in a building, such as a hotel or an office, that are operating on the same channel, and even though they might be on different floors, or they might be, you know, really far away from each other, they still can cause interference. It might be other things. It could be your Bluetooth headset. It could be your microwave. It can be just RF interference getting put out by your industrial equipment, like an air conditioner or some tool out in the warehouse or out in the shop. Those can all produce interference. So we're going to talk here on this slide about how traditionally have we dealt with co-channel interference between access points on the same network. So one of the ways we've done that is you turn down the power, right? We talked about before, your AP is usually a lot more powerful than the client device. So one of the traditional things was if your client device is 60 milliwatts, you'd reduce the power on your access points to 60 milliwatts. So they had a symmetrical relationship as far as signal goes, and that way the AP isn't shooting its signal out halfway across the building where it's not doing any good in theory. Unfortunately, in the real world, that doesn't work so well. And the reason for that is because the signal-to-noise ratio. As you decrease the power of your access point, the received signal-to-noise ratio goes down. So while you have less interference, you've got worse signal-to-noise ratio, and you end up sending less data. So really, there's a little benefit of doing it this way, but it's not the gains that people would think, because you end up losing almost as much on signal-to-noise ratio as you would have due to co-channel interference. So our solution to this is something called Smart Antenna. Us and Ruckus are the only guys that have this. Cisco Meraki does not, Ubiquity does not, Ruckus and us are the only ones that do. So traditionally, an access point has a fixed antenna configuration. So most of your, smoke detector shaped access points these days are optimized to be mounted on a ceiling. So they form sort of an umbrella-shaped dome that radiates out from the access point for the coverage area. If you're doing outdoor coverage and doing point-to-point, you would use a directional antenna which focuses the beam in a certain direction. So what Smart Antenna does, I think it's animating there, maybe, is basically we've developed this smart antenna that can go through literally hundreds of different antenna patterns. And it can optimize them based on where the client device is in relationship to the access point and based on other sources of RF interference, whether they be other access points, microwaves, whatever. Whoops. So basically, when the access point is talking to each client, it will optimize its antenna for that client, both boosting the signal strength to the client and also helping to ignore the areas of space where there might be interference coming in from. And with smart antenna, this works even with mobile devices. So this is a little bit different than beamforming in that it works really well even with mobile devices because we can in real time basically update the antenna pattern based on where the client moves to. So I want to show the benefits here in a real world scenario. So in this case, this is a hotel, could be an office as well. What you see here is we've laid out a bunch of access points in each individual guest room. This is the new trend we're seeing in hospitality, is to have one AP per room, or one per every other room. They're using the 5 gigahertz spectrum, and they've made sure none of the access points are overlapping with their neighbors. But even though they're not overlapping in theory with their neighbors, it turns out for co-channel interference issues, you can have, it just needs to be a really weak signal before you start having issues. Even as poor as negative 79 dB is enough to cause interference. In a clean room environment, or an open air space environment, you're talking literally 1,000 meters or more where you can have interference between access points on the same channel. Obviously, it's a lot less if you've got walls and trees and windows and things like that to deal with. But it's surprising just how far away access points can be from each other and still cause interference. So what we've done here is we took our product, our NWA 1302 Hospitality AP, and we've taken Ubiquity's Hospitality AP, the UAP ACIW, and we tested them in a single AP operating on a channel. We've simulated the throughput of 2 different 2x2 wireless clients connected to that AP. And what we find is basically performance is the same. Hey, well, I'll even say here, Ubiquity beat us by 2 megabits per second, 406 versus 404. And what we see is from an airtime utilization, basically how much of the available airtime is used, it was 67% of what was theoretically there. So not much difference. Now what we've done in the next test is we've turned on this second access point that's going to be causing interference. And this is where the smart antenna really starts to shine. What we see here is the combined throughput, so 2 clients per access point, 2 access points. With smart antenna, we're able to push an aggregated throughput of 785 megabits per second. In the Ubiquity situation, you end up in a situation where it's only 555 megabits per second. And you'll also notice there that the speeds are not evenly distributed on the Ubiquity. The one AP is getting 400 megs, the other AP, the second one's getting 200. Whereas if you look at the smart antenna, you will see both APs are getting right around the same amount of throughput. If we look at channel efficiency, you see we're theoretically exceeding the maximum amount of airtime because the smart antenna is allowing multiple devices to transmit at the same time on different APs without interfering with each other. Whereas you see the Ubiquity airtime maxes out at 95%, basically as good as it's going to get. So now we add a third access point causing interference. And you see we've increased our overall throughput again. We're getting over 900 megabits aggregated throughput on the same channel, where Ubiquity is capped out at under 600 megs. If we looked at the actual airtime usage, or the efficiency of the channel usage, Ubiquity actually went down. It went from 95% with 2 APs down to 91 with 3 APs because of the increased interference and the increased retransmit rate. Whereas we grew again, getting up to 155% of the theoretical maximum because the smart antenna is allowing multiple devices to work at the same time on the same channel. Also, again, look at the speed difference between the two on a per AP basis. With the smart antenna, we're able to evenly distribute that available usage to about around the same 300 megabits per AP, whereas Ubiquity, it's all over the place. And if we had a real world live demo showing as we track this in real time, what you would see is it jumps all over the place between which AP is lucky enough to get that available airtime on the Ubiquiti products. And I'm not picking on Ubiquiti here. This is going to be true with a Meraki product, a Aruba product, any product that's not using smart antenna. And in theory, I'd like to think we're going to perform a little bit better than Ruckus, that we've tweaked our smart antenna better than they have. But in theory, Ruckus should be about the same as what you're seeing here. Because really, it's the smart antenna that's making the difference here. Nothing else about the chipset or hardware. It's all about the smart antenna design. So that's it for smart antenna. I want to start talking here about just some advice for doing installation. And apologies, my voice is starting to fade. So one of the things that we run into here is, it used to be that all the access points had external antennas. These days, it's really hard to find anything with an external antenna because most people are installing these on ceilings, so it's cheaper to manufacture a fixed internal antenna. You also have a lot more flexibility as an engineer, being able to tweak the antenna positioning to maximize coverage. And when we're talking about here dealing with MIMO and multiple spatial streams, it's really important that to maximize performance, that those antennas are fixed. Whereas if you've got external antennas and one might be bent one way and one might be bent another way, you can see some degradation of performance. So that's why most APs now have internal antennas, and generally they're optimized for mounting on the ceiling. So what happens is in a lot of cases, for whatever reason, you cannot mount them on the ceiling. And you end up mounting them on walls, which is fine, but the antenna pattern is designed to be this big umbrella covering down from the ceiling. So when you put it on the wall, what happens is a lot of that signal shoots up to the floor above or gets set down to the floor below. So you're wasting a lot of your coverage space, and if you're dealing with a multi-floor building, you're actually causing interference between the floors because you're sending signal between those floors. So this is something smart antenna can solve. This is also something that we've got some products that have what we call dual antenna, which allow you to switch between a ceiling mount pattern and a wall mount pattern. So you can change the pattern just based on where you've mounted it. Or you can use smart antenna and it will just optimize its pattern based on where the clients are and where noise is. So those are two ways to deal with that when you're dealing with ceiling designed and access point and you're mounting it on the wall instead. So general rule when mounting APs, mount them on the ceiling, and you want to mount them as centrally as possible. You also generally want to mount them as high as possible. And the reason for that is because you want the shortest distance for the signal between the AP and the client device, and you want the least amount of obstructions that you will have. So, you can look at the photo there of cubicles, and you can see, by mounting the access point on the ceiling, you're able to send the signal directly from the client device line of sight to the access point and not having to send it through cubicle walls, through Deborah and accounting, through the printer, things like that. So mounting it higher is generally better within reason. Obviously, some reason you're working in, say, a blimp hangar, you don't need to put it, 400 feet up. That's going to cause some issues there. Same thing goes with expo centers, convention centers, things like that with really high ceilings and really high user density. In those cases, you don't want to mount it so high because you've got a lot of users and you don't want, so you're going to want to lower the access point in those cases. So the coverage area is a smaller area of the floor. You don't want the access point, seeing and getting interference from wireless devices on the other side of the convention center. So those are times when you would lower it a bit. But generally in a typical office or hotel environment, you would want to mount it as high as you conveniently could. Drop ceilings generally have very low attenuation. Basically, the Wi-Fi signal generally passes through those pretty easily. So in those cases where you've got a drop ceiling, don't feel that you have to mount the access point on the drop ceiling itself. Mount it above the drop ceiling so you've got a little extra height, and so it's out of sight. Right, you don't want that AP there blinking and distracting people. You don't want it in, you know, someone's throwing a football around the office on a Friday afternoon. You don't want them hitting the AP. You don't want somebody stealing the AP if it's a public area. So feel free to mount those on top of the drop ceiling. In some cases, people just lay them directly on top of the drop ceiling, and that's fine. If you're mounting them onto the real ceiling above the drop ceiling, one of the issues you might run into is ductwork, lighting, pipes, things like that, which are metal and will either block or reflect the signal. So you might not want to mount them all the way up on the real ceiling if you've got a lot of other metal stuff between the drop ceiling and the real ceiling. So you might want to lower them down or just set them on top of the drop ceiling itself. From a hotel perspective, the traditional way, and you'll still see this being done on a lot of the lower end hotels, is what we call an umbrella coverage. You would mount the access points in the hallway, ideally, and then you would provide coverage from anywhere to 4 to 8 rooms. So the new trend, especially in the higher end hotels, and we're actually even seeing this, something similar when it comes to doing stadiums and concert venues, is instead of providing this umbrella coverage, you're putting 1 AP per room or 1 AP per every other room. Just about everybody out there now has specialized access points just for this scenario that mounts on the wall plate and then has pass-through Ethernet ports for other devices in the room. So the reason we're trending to this type of movement is a couple things. One is everyone now has multiple devices they want to get onto there. You know, in the original days of early days of Wi-Fi in hotel rooms, you know, you'd be covering 4 hotel rooms and you'd have, you know, 2 laptops and a phone trying to connect to that access point. Nowadays, you know, you'll have just one room by itself may have, you know, a laptop, 2 tablets, a Kindle device, and who knows what else, cell phones. So you can have multiple devices in there. So now you start dealing with issues with hidden node problems, interference between the rooms, things like that. And then people are doing more. It used to be that you sat there and you browsed CNN or New York Times or Fox News and read some articles. Maybe you got on some message boards. These days, people are streaming 4K video. So the client devices are eating up more of that airtime that's available. So the way they've solved that and to assure good quality performance in each hotel room is putting in these specially designed per hotel room access points. So one of the things you want to look for is make sure if you're installing these in a hotel room, whether they're specially built or regular, is you want to make sure those access points can be locked in place or very difficult to remove. People will still access points out of hotel rooms if you see them. So it's really important you have some sort of locking mount. You also want to make sure your access point has the ability to turn off LEDs. Nobody wants a green flashing glow in their room when they're trying to get a night's sleep and there's 4 hours of jet lag they're dealing with. So in public areas, you have to take into account user density. You know, a pool area where maybe no one's getting on realistically is getting on the Wi-Fi that much, or if they are, they're just checking email or web pages. We can probably get away with 1 or 2 access points. But if you're dealing with an area such as a lobby just off of the convention center or the convention center itself, you may need a lot of access points on there because you've got a lot of clients. So that's what you want to take into account. How many clients am I likely to have in this area are going to be online at a time, and what are they going to be doing? The more clients or the more bandwidth intensive tasks they're going to be doing, the more access points you're going to need. And that's where a smart antenna really plays a huge factor into things. It makes a world of difference in a convention center space or any space where there's a lot of users or a lot of really demanding bandwidth applications. Use load balancing. Use client steering to help make sure clients aren't all connecting to the one access point, and to try to steer clients across the multiple radios in those access points. Different areas should have their own coverage. So even if the lobby and the hotel bar are right next to each other, they should each have their own access point, and possibly even be VLAN'd off from each other. But smart antenna makes a world of difference in these situations. For schools, I mean, the first question you need to ask is how many students are going to be in each of those classrooms, and are they all of them going to be online? So there's a world of difference if you're in a new up-and-coming school district where every student has a Chromebook or a tablet and they all get online and use smart whiteboards and things like that. That's going to be a different sort of use scenario than if you've got a more traditional classroom that are using books and they're only getting on Wi-Fi for certain lessons or in downtime, in study periods, things like that. And then you need to know, what are they using those laptops for? Are they just using them to upload homework assignments or check a message board? Or is the teacher streaming video to each one of those devices or pushing images out to them? So that's going to determine what's going on. So you'll use those factors to determine how many access points they need. So generally, teachers and students should be on their own SSID VLAN off from each other. And only allow communication from the teacher to the student VLAN for pushing video and things like that out. Generally, we suggest in a connected smart classroom where every student has a device, using 2 access points per classroom. Again, this isn't a limitation on the hardware. It doesn't matter if you're using our cheap APs or our expensive APs. It has to do with 802.11 and interference and the fact that only one device can in theory transmit at a time. So use two APs, and if you're using our equipment, we have a special load balancing mode both in our cloud APs and in our controller APs that's specifically designed just for smart classroom use. And then if you've got 30 or more students in the classroom, you absolutely need to use hardware that's got smart antenna built into it. So next up here for us, what's the deal with 802.11ax? You will see products out there being advertised as 802.11ax today. They're not. So let's talk about it a little bit here. So 802.11ax has also been being called Wi-Fi 6 by the Wi-Fi Alliance. You will also see some people calling it high efficiency wireless. It's all the same thing. Basically, you know, we talked about all those issues with 802.11 and the protocol and how it limits the number of devices, how it limits airtime and throughput. 802.11ax is designed to fix that for you. We've completely reworked Wi-Fi and how it functions. So 802.11ax will work on both 2.4 and 5 gigahertz radios and any additional radios you may have or wireless frequencies that may come along in the future. So basically, it increases QAM, like we talked about, from 256 to 1024. A really cool thing it's done is it's added OFDMA. So OFDMA, instead of having the clients try to guess when no one else is wanting to talk, allows the access point or router to specifically allocate different chunks of airtime for specific clients. So it can say, hey, you over there, you've got access, transmit now. This is your chance. So it makes much more efficient use of the airtime, dramatically reduces the amount of retransmits and drop packets that you're going to see. It now allows MIMO, so the ability to use multiple spatial streams, not just to have your access point send data to multiple clients, but it will allow multiple clients to transmit at the same time using different spatial streams at the same time. There's spatial frequency reuse. There's a whole bunch of other cool stuff that it's doing. So here's the thing. The last time I checked, which was about a month ago, the official 802.11ax standard still isn't set to be ratified until January 2020, or to be approved. The working group spec to be approved then, and then to officially be approved by the wider IEEE isn't scheduled until March 2020. So anything that's claiming to be based on 802.11ax is based on the draft spec that's out there. Some of you older people may remember with 802.11, 802.11ac, a lot of hardware vendors pushed out draft compliant hardware and promised it would be firmware upgradable to the final spec. In most cases, it wasn't, and we're seeing the same thing with 802.11ax. These chips that are out there right now are, most of them, or I think all of them actually, are not going to be able to take full advantage of 802.11ax. They are missing some features that will be part of the official chipsets. So if you buy something that's 802.11ax today, when the final spec is done and out there, there will be features that you will not be able to take advantage of that will hinder performance of your network. In theory, the chips that come out in Q3, Q4, at the end of the year, the hardware then using those new chips, such as the Qualcomm, their 2.0 chip, those in theory, the silicon should be able to support all of the draft features unless there's some major changes, which isn't likely. But the stuff that's out there today, I don't believe any of it supports all of the features that are out there. I think Qualcomm is shooting for end of Q3, Q4 for their chip that supports it all, and Broadcom, I think, is shooting for August. That's the last I heard. The other important thing is, in order to use all these new cool features of 802.11ax, your client devices need to support 802.11ax. And the chipset vendors aren't even expecting to have reference chips out there until the end of 2020. So if you run out there and buy 802.11ax today, you aren't going to be able to take advantage of everything. If you go out and buy it at the end of the year with the new chipsets, in theory, you'll be able to take advantage of everything, but you're still looking at easily, 1 year before you'll even have a single client device that can actually use those new 802.11ax features. And realistically, widespread adoption is probably 2021, 2022. I'm sure Apple will probably be 2021 or 2022 before they support it on their tablets and things like that. So that's it for today's presentation. Any questions, send them in via the Q&A window. I will try to answer them for you. Just to want to make sure everyone knows about this, we do have online forums. Our R&D and CSO teams from our headquarters monitor those forums, and we'll jump in and answer questions there. So if you don't need to talk to a live person with an issue you're having, or you've got some feedback or user suggestions, or you just want to chat with other Zyxel users or resellers, forum.zyxel.com will take you there. And then just in general, if you have any offline questions you want to send me, if you have any suggestions for future topics that you'd like to see us do a webinar or training on, or you just want to give me feedback on how I did today, you can email me directly. It's right there on the screen, seanr@zyxel.com, or you can funnel it through your salesperson if you want to be a little bit more anonymous. Okay, so first question up is from Anonymous. Anonymous is asking for multi-user MIMO. Does the client device need to support multi-user MIMO or MIMO? So that's a good question. So this is a common thing where people get confused. So generally, MIMO is referring to being able to combine multiple spatial streams together and aggregate the throughput. So that's why a 2x2 device on 2.4 would theoretically get up to 300 megabits. So to support multi-user MIMO, the client devices need to also support multi-user MIMO. So multi-user MIMO is a separate thing from just standard MIMO. So anything that the 802.11ac these days supports MIMO to some extent. Not everything supports multi-user MIMO. Multi-user MIMO was actually rolled out a good 2 years after most of the 802.11ac draft stuff started hitting the market, and it was a little bit later on the client devices. So yes, not only does your AP or router need to support multi-user MIMO, client devices need to support multi-user MIMO to be able to take advantage of multi-user MIMO. If you've got mixed environment where some devices don't support multi-user MIMO, that's fine. Those devices will just use the regular, maximum throughput they can get. Okay, that was it for questions so far. Again, send them in via Q&A. I've got a question here in chat from Mark asking if it will be recorded. And yes, this has been recorded. It will be posted to our website here in the next few days. And I've already done this presentation once before, so that recording should be up now if you want to watch it. If you're having trouble finding the recordings, and I don't blame you, our website is not always the easiest thing to find stuff on, reach out to your salesperson and they'll provide you the direct link. Okay, so another anonymous question's come in here. It's asking about, other than classrooms, when do you recommend using separate SSIDs for coverage areas? So basically, you use separate SSIDs anytime you want to restrict access to certain users to certain network resources. So the most common usage of this is going to be guest access. If you're providing guest access, whether it's an office or a hotel, you generally want the guests isolated from your internal employee usage. So you'll have those on different VLANs. In some businesses, the sales guys will be on a different VLAN from the admin team, which will be on a different VLAN from the ops team. So same thing, you would give them each their own SSID and VLAN them to isolate them and restrict which network resources they have access to. If you're doing anything with PCI, so if you're doing any sort of credit card processing, whichever devices are accessing the credit card processor and seeing that credit card information, those absolutely have to be on their own VLAN separated from anything else, or else you will not pass PCI compliance checks. So I hope that works. That explains some things there. So we've got a question here from James. For residential application suggestions on where to mount, basement pointing up, top floor. For consumer stuff, generally what you're going to want to do is if you've got a 3-floor building, you're going to want to put it, and you're only putting in one device, you're going to want to put it on that middle floor. That's going to give you the best chance at covering the floor above and the floor below. Although realistically on most bigger houses, one AP or one router is not going to be enough. So you're either going to want to run Ethernet and put additional access points around. You might want to use something like power line technology and provide a Ethernet port, and anything that's going to be bandwidth demanding, such as a game console or a video streaming device. Probably the most popular things these days are these mesh products. So from Zyxel, they're called Multi-U and Multi-X. And these basically, you have one router that you plug into your Ethernet connection, and then you have multiple satellites you can distribute around the house to share and boost the signal. So my one big point of advice when dealing with these is you absolutely want to get a tri-band mesh system. Problems with something that's not tri-band, such as the Google Mesh, is they're using the same 5 gigahertz channel and radio to create the link between the satellites and the main router as they're using to communicate with the client devices. So that means you're dramatically decreasing the available bandwidth, because what happens is the client device takes the airtime to send its data to the satellite, and then the satellite takes that data and needs its own dedicated airtime to then relay that information to your router or your internet connection. So in a tri-band system, you've got a dedicated radio and a dedicated channel that's only being used for the backhaul. So you don't have that massive bandwidth hit that you do on a dual band mesh system. So most of the really cheap mesh systems in the Google system are all dual radio. Most of the newer systems that are out there are tri-band. So you want tri-band, whether it's us or Victor's Orbi or whatever, you want to make sure you're doing tri-band. And to make things even more confusing, some of the vendors out there have now got situations where the main router is tri-band, but the satellites are dual band. So basically that third radio in the router doesn't get used. So you want to make sure the satellites are tri-band as well as the router itself. So you want, trust me, you want a tri-band system, especially if you want to future-proof yourself against video streaming and you want to future-proof yourself for playing video games online. The next big thing that's being hyped up is video game streaming. There's a number of new consoles coming where the hardware is basically just a set-top box, and all the rendering is being done in the cloud and then being streamed to the TV that way. This fall, you will see a lot of devices doing that. So that's just one more thing. It's going to eat up a lot of bandwidth. And with gaming, it's really latency sensitive. So if you've only got a dual band mesh system in your home, you're going to be hating life when your kid goes to play games on that new streaming system in the fall. Okay, next question. Jack. In the case of multiple access points, how is load balancing configured and handled? So that's a good question. It's going to depend on whose equipment you're using and how you've got them set up. We've got load balancing through our controllers. So whether you're using a dedicated NXC controller or using one of our USG's security gateways that also has the wireless controller built in, you can control it that way. If you are doing Nebula's got the settings in there on how to set up load balancing and things like that. It's probably too in-depth to talk about different theories on how to do load balancing. Generally, most people just turn it on and that's good enough. If you've got a really tough, dense environment, you might want to do segmentation of the different, segmenting your network out and doing load balancing just internally within those segments. But most of those work. Some standalone equipment out there claims to do load balancing, and it works okay, but generally you need a cloud or a hardware-based controller of some sort to get it to really work well. Let's see, we've got, I think, another question. Sorry, I'm having issues here with my box. So yeah, Nebula absolutely does both load balancing and does channel steering. Those are features you can turn on. So let me, before I go to the next question, let me also delve into that a little bit more. So 802.11, before 802.11ax, has come out with some new standards to help both with roaming, to help with load balancing and steering and things like that. So those are known as 802.11r, 802.11n, and my mind is going blank. I'm sorry on what the other one is. So those are all supported by Nebula, and those are all supported by our controllers these days. So you can turn those on. But again, it requires that the client device support those. So if your client device doesn't support 802.11r or 802.11n, it doesn't really make much difference if you turn it on or not. So we also have the functionality to go in there and sort of force it from the AP with a hack to force those client devices that don't support the standards to sort of do it. So one of the ways we help force roaming, and this is going to be really big if you're using an older iPhone. So one of the problems with older iPhones and a lot of other devices is roaming by the original 802.11 standards is handled entirely by the client device. It's the client device that's supposed to be scanning the RF environment. It's the client device that's supposed to say, hey, wait a minute, this AP has a better signal strength. I should roam to this other access point. But that's dependent on the client device. And I like to use iPhones because most iPhone users have experienced this in a multiple AP environment, especially like the iPhone 6, was you'd come in, you'd connect to the first AP closest to the front door, then you'd walk to the back of the house or the back of the office, and you'd still be connected to that AP, even though there's multiple APs between you and that. They did not, a lot of client devices did a really horrible job when it comes to roaming and don't really roam unless they absolutely lose the connection. So one of the things we can do in the interface is we can go in there and we can say from the access point perspective, when the signal gets below this certain threshold, kick that guy off there and don't let them reconnect for, you know, a few milliseconds. So in theory, and it works pretty well, is what happens is the client device gets disconnected. It'll try to reconnect and it'll be told, no, you can't connect yet. And instead it'll go, oh, maybe I should look at the RF and see if there's another AP I can connect to. And then it'll connect to the better AP. So that's one way we have of forcing roaming between devices. We do something similar when it comes to steering. We can steer client devices and basically say, this radio's got too many users, or this AP's got too many users. We're not going to let this guy reconnect. We're going to not let him connect. And we'll wait a certain number of tries, 3 tries or 5 tries, to try to force them to roam to another device. And then we say, okay, well, they've tried, they keep connecting to us. Clearly, they're not going to roam. Okay, now we'll let them connect. And for the most part, it's seamless behind the scenes. It's just a few milliseconds delay, generally, when it comes to handshaking and stuff. So those are some of the things we do to help deal with those older client devices that don't support the standards when it comes to steering and roaming. Another question here from James is, would ceiling or wall mount be best? So again, generally, ceiling mount is the best, simply because most APs with internal antennas are optimized with the assumption that you are mounting them smack dab in the middle of the clients up on the ceiling pointing down towards them. So that's going to be best just for that reason alone. Like I talked about earlier, you know, we've got certain APs that have the dual switchable antennas, where we've got built 2 different sets of antennas internally into the device. one optimized for ceiling, one optimized for wall. You can switch between those. And in the case of smart antenna, it doesn't really matter that much because we've got so many different antenna patterns. Plenty of them will work just fine on wall mount, although ideally you'd still want to do ceiling mount if you could. So I hope that helps, guys. I am going to stop the recording now. I will stick around for another couple minutes. If you have any questions,